Welcome to this explainer, brought to you by Forge College. I am absolutely thrilled to be your guide today. Now, if you've been following along with our track on transitioning from EVM to SVM, you know we're right in the thick of application development with cost models. Today, we're going to zero in on a really crucial topic, profiling and optimizing transactions. We're going to learn exactly how to take your transactions, put them under a microscope, and systematically trim away all that excess compute unit fat. So, let's just jump right in.
Okay, so let's set the stage. If you recall our previous explainer, incorporating cost estimates into development workflows, we actually did some pretty fantastic foundational work. You successfully integrated a cost estimation script right into your continuous integration pipeline. Think of that script as the ultimate magnifying glass for the detective work we're about to do today. You now have this concrete output, right? A CSV or JSON file that captures the exact compute unit consumption per instruction group, along with timestamps and input parameters. So today, we are moving from simply measuring the cost to actively taking action to reduce it.
To pull this off systematically, here is our Optimization Detective's blueprint. We'll be walking through 5 steps today: establishing the baseline, finding the hot path, applying micro-optimizations, measuring the impact, and iterating for stability.
Let's start with step 1, establishing the baseline.
Every good investigation, whether it's a literal crime scene or just a bloated code base, starts with a clean scene and a highly reliable baseline measurement. Without a baseline, any optimization you make is literally just a shot in the dark. So, to get that perfectly clean scene, we have to be strict. First, you must reset your local validator. If you're using Solana's local test validator, for instance, you really want to clear any previous state so your baseline is perfectly repeatable. Second, deploy your program. And third, run your estimation harness at least 5 times. Why 5? Well, because we need to capture multiple per-run compute totals to account for any random system noise. This gives us the rock-solid starting point we absolutely need for our optimization decisions.
Moving right along to step 2, finding the hot path. Now that we have our baseline data securely logged, we need to map the profiler's raw data directly back to our source code. We are looking for the exact lines of code where our precious compute budget is draining away. We're hunting for the hot path. Think of the hot path as our primary suspect. It's the specific execution route in your code where compute units concentrate the absolute most. This is usually caused by repeated actions or unnecessarily expensive operations. Basically, it's the mechanism creating the most friction in your application, and therefore it's our biggest opportunity for massive savings.
Tracing a transaction execution timeline illustrates this perfectly. Let's say at 0 milliseconds, we initialize execution. At 5 milliseconds, maybe we have a double account deserialization. I mean, it's not great, but it's not terrible either. But look at the 45 millisecond mark. We hit a repeated hashing loop. That right there, that is our hot path. A seemingly innocent loop in your code can secretly hoard the vast majority of your compute units if it's doing complex cryptographic work over and over and over again. We need to catch it in the act.
Which brings us to step 3, applying micro-optimizations.
Okay, we've found the friction point, so what do? Well, it's time to apply some targeted oil to the gears rather than tearing down the entire factory. Look, I know exactly how developers think. The second we see a piece of inefficient code, the overwhelming urge is to rip out the entire foundation and rewrite the whole architecture from scratch. It is so tempting, but we really have to resist that urge. Right now, we want a micro-optimization, not an architectural refactor. We only want small, reversible, and highly measurable edits. Because think about it, if you change too much at once, you're never going to know which edit actually saved the compute units.
So, what does a micro-optimization look like in practice? Here are a few really practical strategies to reduce repeated work. First up, you can cache deserialized account data. Instead of reading and deserializing a structure over and over inside a loop, just read it once outside the loop and reference it in memory. Simple. Second, avoid redundant hashing. If you can compute a digest once, do it, and then just reuse it. Third, batch your state writes. You can accumulate your results in memory and perform fewer combined writes to the state. These are small, surgical tweaks, but they lead to absolutely massive compute savings.
Now, on to step 4, measuring the impact.
We've applied our fix, but a true detective doesn't just assume the case is closed. A true detective needs hard, undeniable evidence that the optimization actually worked. We must apply the scientific method here. First, rebuild and redeploy your program to the local validator. Second, and I can't stress this enough, this is incredibly important, you must run your estimation command with the exact same identical inputs and the exact same number of reps as your baseline. If you change the inputs even a little bit, the comparison is entirely meaningless.
Finally, compare your new optimized JSON data against your original baseline JSON data.
So what does a victory actually look like on paper? Well, comparing our baseline median compute units of 10,200 to our optimized 8,300 yields an 18.6% reduction. That's huge. Furthermore, our interquartile range, or IQR, dropped from 200 to 150, which means our results are tightly clustered and consistent. And of course, 5 out of 5 reproducible runs passed. Because the drop in compute units significantly exceeds the IQR variance, we have actual statistical proof that our compute savings are real and not just a fluke.
Almost done. Step 5. Iterating for stability. Don't celebrate just yet. The final step of our investigation is ensuring that our victory is actually stable and not just some weird transient behavior in the local system environment. It is surprisingly easy to fool yourself when optimizing, so here are the common traps that can skew your evidence. First, comparing different transaction inputs. We just talked about that. Keep them identical. Second, state bleed from previous runs. If you don't reset your validator between comparisons, leftover state might artificially favor the optimized path. Third, JIT warmup or caching effects. Sometimes the runtime caches things, making subsequent runs look artificially fast. Just restart the validator to clear this. And finally, scope creep. Doing too much at once completely breaks your ability to attribute the savings.
So the absolutely crucial takeaway here is summarized in this guiding philosophy. Prefer narrow micro-optimizations over large architectural refactors. If you keep your changes narrow, you can perfectly statistically attribute the exact compute savings to your specific tiny edit. It's only if profiling later shows broad systemic costs across the entire board that you should then consider the heavy lifting of a macro refactor. This has been a really fantastic look at the micro level of optimization. But what comes next? Well, in our upcoming explainer, we're going to explore operationalizing cost models and scaling implications. We're going to take these one-off optimization experiments we learned today and embed them directly into standard, continuous integration and monitoring operations. That way, they become automatic guardrails for your entire dev team. Before we wrap up, I want to leave you with a somewhat provocative thought to chew on. What if you trace your hot path and you find that it's purely essential business logic, something that absolutely cannot be cached, unrolled, or batched? At what point does a micro-optimization reach its absolute limit, demanding a total macro refactor of your architecture? It's a tough engineering question that, honestly, every Web3 developer eventually has to face. Thank you so much for joining me for this explainer, brought to you by Forge College. To master these concepts and dive even deeper into Web3 development, make sure you visit forge.college. I will see you in the next one.